What's generalized force?
What is the force?
And then Jesse started cracking up. That was great.
Where have I put my
Because he didn't know how to
stuff?
put the generalized force in for the damping, and then he said, look at the last one.
Oh
I
man,
was like, what if I got the last question?
where'd I? This is not one of those days I can do without my notes. I need my notes.
I love Jesse's attitude. He's great.
All right. Good news, I found the notes. I think. Oh man, wait, what? Here they are. Well, almost. Okay, we got it. I'll begin with a word of prayer. Dear Heavenly Father, we thank you again for your many blessings to us, and just ask that you'd guide our steps today. Help us to wrap this material up so we can start the break. In your name I pray, Lord Jesus. Amen. All right, so talk about magnetism today, of course. And so I have just kind of a few small comments to make here. One is that the net force on a current loop is zero, right? We talk about that. Net force of a current loop under a magnetic field, the net force on it's zero, assuming the magnetic field's uniform. But if the magnetic field's not uniform, it turns out that the force can be calculated from like the gradient of the dipole moment of the current dot the magnetic field applied. And that doesn't have to be zero, all right? And Griffith points out that this is actually in good agreement with the force that was put on a dipole in the electric sense, in the presence of a, electric field. So that was like the force that was on an electric dipole before. So it's neat, and that's the same kind of thing. Example 1, he works out in some detail that if you look at like the sort of like the electron orbit, say with velocity v, and of course it's orbiting around, we can think about plus e in the middle, but I don't mean a positron, I mean like the nucleus. Man, I wonder if there's going to be a market for a course in particle physics here in a few years. Whoa. That wasn't just me, right? Did you guys see that blink?
Yeah, what?
I saw the lights dim. Yeah. Huh. Well, let's get this done. So magnetic field like so, right? And he goes through and he derives with the sort of like electron cloud model or whatever, that if you switch on the magnetic field, then the change in the electron speeds up, and the change in the velocity is something like ERB over 2me, the mass of the electron. Radius of the electron orbit, that's the charge of the electron right there. And as Griffith says on page 273 to 274, he says when the magnetic field turns on, the electron speeds up. And in this context, the change in the, so here I'm saying the dipole moment corresponding to the electron current, right? It's minus 1/2 e times the change in the velocity here, r z hat. In other words, it's minus e squared r squared over 4me times the magnetic field applied. So the key point that I want to make here is simply this, is that this in some sense will explain diamagnetism, right? So like the dipole moment induced from B is opposite the applied magnetic field, right? And so we said there were three kinds of materials. There were I feel like I'm saying this wrong, but diamagnetic materials, paramagnetic materials, and also ferromagnetic materials. So like the diamagnetic, the induced, the magnetic monopole, excuse me, monopole, listen to me. Golly. The magnetization is opposite the B field. For a paramagnetic, the magnetization is the same direction as the B field. And for a ferromagnet, it's got some kind of permanent magnetization, which is a more complicated story. All right, its magnetization can be independent of the B field to start with. Like it's a process. It can get aligned any old way, I think. Anyway, that's a more complicated story. But let me remind you that we had a definition, which we need to think more about today, which is that M, big M, is equal to the dipole, magnetic dipole moment per unit volume. All right. Now, this magnetization, again, it can come from diamagnetism, paramagnetism, or ferromagnetism. Diamagnetic things include like water, copper, gold, graphite, bismuth. Paramagnets include aluminum, platinum, liquid oxygen, a bunch of other stuff. Ferromagnetic stuff, he only gives 3. He says iron, nickel, and cobalt. Those are your permanent magnets. They can be permanent magnets at least, right? You can find places on Earth where rocks that are in the ground have, like magnetism because they've got so much iron ore in them or whatever. All right. So we need to derive the bound currents. All right. So let's go through that. Bound current derivation. So I will remind you, suppose we're given a material with magnetization M over some volume V. So then we can calculate the vector potential due to that in magnetization as follows. We simply integrate the dipoles, magnetic dipoles, and we add together their contributions to the vector potential like this using superposition. All right. Stuart's missing a prime on the initial tau, but whatever. All right. Now, we can trade that for mu naught over 4 pi, the integral of m of r prime cross nabla of 1 over script r. But not just nabla, we need nabla prime. Now here, nabla prime, you may remember, is x hat prime partial x prime plus y hat prime partial y prime plus z hat prime partial z prime. This is the gradient operator with respect to the integration coordinates. All right. Yeah?
Is that r squared applied to just the r hat, or applied to that whole?
Well, that's just a cross product. So like this is just a scalar multiple of 1 over r squared, so I can bring it in to there, and there's an identity that the cross product, like the nabla prime of 1 over script r is equal to script r over r squared. So like, if you want, I could go up here and I could rewrite that as this, if you prefer. That's all that's going on there. Now, of course, the script r squared is like, x minus x prime squared, y minus y prime squared plus z minus z prime squared, right? So if you look at the derivative with respect to the prime, you pick up a minus, right? From this, as you do the chain rule. So you end up with a minus there, but then there's another minus from the derivative of the reciprocal function. Those minuses cancel and leave us with that. So we talked about this before. I think it came up in the similar derivation of like the bound volume charge and the bound surface charge for the polarization. That part we did similar, almost the same mathematics, really. So look here then. I can trade this for mu naught over 4 pi, big parentheses. Let me do the product rule over here. I like to actually show the product rule, so you'll forgive me for doing that. The curl of 1 over script r times m. I'm going to omit the r of r prime dependence if you guys don't mind. That's equal to 1 over script r curl prime of m minus m cross product with the gradient prime of 1 over r. That's just the product rule from the front cover, right? And so, like, look at what we're at. We have this to start with, right? Over there. So I can trade this for the integral. These are all integrals over v, right? I can trade it for the integral of 1 over script r cross product, curl prime of m minus curl prime of 1 over r m d tau prime, I think. Let me double check on my, yeah. So that we can then rewrite as mu naught over 4 pi, the integral over the volume of del prime cross m, all right, divided by script r, d tau prime, plus mu naught over 4 pi, the integral over the boundary of the volume of 1 over, well, m of r prime. Let me omit the r prime dependence to make things prettier. M cross dA prime divided by script r. Or maybe it's even better to write it this way. This is m cross n hat times dA. We could write it like that. Now you notice that I've gone from a volume integral to a surface integral, and it's not at all obvious going from here to here. You have to you have to see homework problem 1.61b to understand that, which I probably should have assigned. I don't feel like I did though. I was on the cusp of giving you guys that homework problem, and I thought, we don't need that. No, we need everything. Everything in chapter 1 you eventually need at some point. Hopefully, except for that problem we never figured out. But probably we don't need that one. So, I mean, the proof going from here to here, it's got to involve like the divergence theorem somehow or another, right? Because you're trading a volume integral for a surface integral, basically. So, anyway, that is homework 1.61b that establishes that step, which I don't want to derail class to do a homework problem I didn't assign you guys. You'll forgive me. But once you do that, then you tilt your head and squint and see that this is mu naught over 4 pi, the integral of jb over script r. I'll put the r prime back in for good measure now. D tau prime plus mu naught over 4 pi, the integral over the boundary of the volume of kb at r prime divided by script r dA, where we have defined the bound current density as the curl of the magnetization and the bound surface current density as the magnetization dot, listen to me, there's no dot products anywhere here, crossed within unit normal. So these are definitions. Aye. So example 2, I'll try to run through this real fast. We had sphere, radius r, right, with magnetization m equals to just mz hat, all right? So in this case, what's the bound current? What's the surface current? Hi, you keep doing dot products. What is wrong with me? Good night. So how about the bound current here? This is a constant magnetization, right? Constant, I'm saying there's a constant magnetization over the sphere. So what's the curl is 0, right? There's no bound, there's no interior current, right? On the other hand, the surface current, we can calculate a little bit more explicitly like this. This is m, you know, z hat is 0, 0, 1. And n hat is what? It's r hat, right? The spherical unit. So that's cosine. Oh goodness, you will not get me, sir. Phi, sine theta, sine phi, sine theta, cosine theta. Take this here cross product, what you got? All right. To get the x, we do z cross y, but that's minus sine phi sine theta. And then you've got cosine phi sine theta, and you got 0 for your z component. Now factor out the sine theta from that. You got m sine theta minus sine phi cosine phi 0. And that is phi hat. So what we have then is m sine theta phi hat. So I wrote that down last time, but I didn't explain it, and I felt kind of guilty for not going through these details, so there they are. So in this, reminder, we worked the spinning, you know, uniformly charged ball, right, last time, and the surface current there was sigma v, which was equal to sigma omega r sine theta phi hat, right? So this is from, you know, from previous lecture. From lecture, what lecture am I on? From lecture 20, all right, from last time. Which is incidentally from like chapter 5 of Griffiths. So as you look, so here's my bound current, right? So you can see that it's the same problem, right? And as such, we've already worked out the magnetic field. Last time, it was very involved. Like, it was horrible. But that is this apparently what we should identify with M. So we simply substitute, you know, M equals to sigma omega r into, you know, previous result. And the previous result was that the magnetic field that results from that surface charge spinning is, oh goodness gracious, mu naught, my bad, there's 2/3. It was a 2/3 mu naught sigma r omega z hat. So making our, hey, it's the same math, let's use the, we already did, step here. This is 2/3 mu naught m z hat. In other words, 2/3 mu naught m vector. So there you go, that's the magnetic field for r less than or equal to r. And so like the magnetic field's uniform, and basically it just looks like this inside, okay? Like here's my field lines, like that. Then what happens outside of the sphere is that it's like a pure dipole at the origin. So I think, if my intuition's not completely cooked, in a bad way, that, you know, it should do something like this, I guess. You know? Whee! Well, those are supposed to be vertical inside, and at no point did a field line start and stop here. They're actually, I think this problem is not the one we're looking for, right? It's not the 30-point not closed loop problem that I have offered. 30 points to earn. Find me a nice, clean, basic example where I don't have to use numerical methods.
You didn't say basic.
I'm interested in this for future purposes. Like, I'd like to give this example when I teach Physics 232. I'd like to go, this is an example we can understand with Physics 232 where the magnetic field lines are not closed loops. So ideally, there would be a Physics 232 level explanation of why they're not closed loops. Now, it doesn't have to be an ironclad mathematical explanation, but it does have to be convincing to an audience of arrogant engineers. So, or, I mean, they don't have to be arrogant, but like they're amongst you guys, right? They walk among you. Like, know-it-allism is a thing, right? We used to live next to an engineer when I was growing up, and he was arguing with my mother once about the order of the letters in the alphabet. Like, for some reason, he had like the order mixed up, and he was arguing my mom was wrong. But we're talking about A, B, C, D, E, F, G, H, I, J, K, L, M, N, P, Q, R, S, T, W. You know the deal. I don't know what the letter was that he was arguing about, but you know, that's the kind of confidence we're talking about, right? The confidence to believe that you know the alphabet better than the mom teaching her kids next door. Maybe you're wrong. Anyway. All right, so there's that. Now, this is, of course, I'm going to erase this, but this is a mathematical derivation, obviously, of the bound current and bound surface current, right? But that doesn't really answer the question of how is that happening, right? Like, where is this bound current coming from? And so there, we can draw a picture which might be convincing to you. I'm only going to do half of it. I'm going to do the easy half. I mean, I'm going to claim the other part, but if you guys have not noticed, I'm getting lazier as the course goes on. Okay, so let me attempt to draw the picture. Physically. All right, so imagine you've got some kind of like slab. All right. And to keep things simple, we'll just think about it like it's one atom, like one molecule deep, just to keep things relatively simple. And then we imagine we have the magnetization is like this, all right? I want to explain where a magnetization like that can come from. It can come from the orbital electrons all being more or less aligned. So, like, maybe there's one here, and there's one there, there's one here. I'm trying to make these big enough that I don't go nuts drawing them. Like, we'd like to do more today than just draw this picture. This one, we'll make this one really big there. Anyway, the point is that these are all, I'm just trying to illustrate like the orbit of the electron around the nucleus. And so if the magnetization is like that, they've got this kind of current loop. So it's like here. And then, all right, so of course that it's a loop, so it comes back down like that and around and down and around, 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 around. Of course, it comes back down, back down, back down, back down, back down, back down. All right. And then similar story down here, right? All right. So it's got to come like this here. My point is that if you had all these orbitals, if you have these orbitals, their collective, the collective dipole moment, magnetic dipole moment that they make is an upward pointing one. All right? So what I'm trying to say is that this collection of like hypothetical molecules, it comports well with my magnetization. Like this is a potential way you could have that kind of magnetization set up for the solid, all right? But you notice what's happening with these current loops, right? Yeah, all the insides, they be canceling, right? Oopsie, don't do that. Don't look too hard at my Calc 3 notes. There'll always be like one, I have these pictures, and there's always like the one. Sam will be like, what's with, did I do it? This one? This one? Good grief. Okay.
So the first three on the left are good, and all the rest are like...
Oh man, good night. Jeez. See, I shouldn't try to talk and draw. I should just like content myself to, you know. All right. Oh man, which one? Where?
Start at the bottom left.
Ah! Which one? Oh, this one too. And this was after you guys corrected me. Good night. So like, I don't know, my mom pulled me out of public school when I was in first grade because the teacher said I was dyslexic. Maybe she was right. Oh, come on. Tell me I didn't have the camera. Please, 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 please do be on the right board. Yes, okay, good. Like this is if I went through all of that with it being on the other board, that would have been particularly horrible. All right, anyway, let's get this over with here. So the point is, yes, all the interior currents cancel, right? And it's as if you've got this, you know, current that goes like this around the edge. And, you know, if you were to look at the n hat here, right, you can see that this suggests that the bound surface current is m cross n hat. That gives the right direction. If I do m and I cross into n hat, into the board, which is what we're seeing there. And you can check other points. So that's why the bound surface current works like the magnetization across the normal. Now, the other formula is more involved. You have to look at like little adjacent cubes and sort of quantify what it means for the curl to be different. It would, in order to understand that, you'd have to think about non-uniform magnetization. And if you look at page 280 to 281, he derives it there. It's more involved. Like I can't do it on the fly, and I unfortunately didn't have time. Just to be frank with you guys, I didn't have time to work this out at a level I can understand it, explain it to you. But it is, I think, a reasonable explanation on page 280 to 281 in Griffith for that. Now, one thing I can explain to you is that this does give us a steady current. Like the divergence of the bound current, right, is the divergence of a curl. And that is 0. So indeed, and that's not really surprising, right? Because whatever the bound current is, and the bound surface current, and also the bound volume current, it's a property of the magnetization, which is not time varying, right? It's uniform magnetization. I mean, well, it doesn't have to be uniform magnetization, but it's not surprising to me that these like bound currents are steady. It'd be really weird if the magnetization, right, produced currents which were not steady. That would be wild, wouldn't it? You know? There are probably such materials, right? But, all right, so that brings us, actually I'm gonna do what I should have done like a while ago, which is shut these stupid blinds. They make every board but the middle one unusable in here. Because like when you go watch the video later, it's like totally like, oh man, that's bright. Do you guys know how much brighter the light is outside versus inside on a day like today? Like in terms of intensity, how many times do you think the intensity of light is outside versus inside? 10 times? What do you think, Sam? 10 times? Something like 10,000 times. So sunlight compared to typical room lighting is incomparable. So when you try to like take a video in a room where you've got just a little bit of sunlight. Yeah, visible spectrum. Yeah. Yeah, granted, the sun is dumping all kinds of stuff that hopefully these lights aren't producing, right? Like we need to supplement our interior lighting with some like UV lights maybe, so the students can get a tan inside, that kind of thing, you know? Probably you'd eventually get sued over that, you know? All right, so next we must talk about, this is one of the things that when it catches me off guard, like is very annoying. Because if you look in a book about magnetism and like Maxwell's equations and stuff, you will find that there's a lot of books that call the thing we're about to call H, they'll call it the magnetic field. Now Griffiths calls it the quote-unquote auxiliary field, but I think if you read more carefully, you'll see he actually says basically, I'm not going to call it anything, I will call it H. And that is also my practice. It's the H field. All right, I mean, perhaps it should be called the magnetic displacement. Like we called the big D was the electric displacement. This is the analog of that. All right. So given a material with both bound and free current rather. So the bound, this is due to the magnetization, and this is due to experimenter, right? Or engineer, whoever has conspired to put a current source to pass a current through something, all right? We usually have control of the free current through experimental setups, yeah? Well, if that's the case, then the total current, J, is a sum of the bound current and the free current, all right? And Ampere's law says that the curl of the magnetic field, by the way, bound current's a steady current. I'm assuming the free current's also steady, so Ampere's law applies to the total current. The curl of B is mu naught times J, right? Okay, but this is actually mu naught times what? Now J bound is what? It's the curl of the magnetization, right? Plus the free current. So, all right. So this suggests then that the curl of what? If we take 1 over mu naught, put it with the B, subtract m to the other side, right? That would be equal to the free current. So I divided mu naught to the other side, and then I subtracted m to the other side and used the linearity of the curl. Well, guess what? This is by definition H. The auxiliary field is by definition 1 over mu naught times the magnetic field minus the magnetization. Oop. Definition. Now once we make that definition, like what happens? We have that the curl of this H is equal to the free current density, right? That is Ampere's law for the auxiliary field, right? I don't like just saying auxiliary field because it has, I feel like magnetism should somehow appear in the whatever we're calling this thing. Like electric displacement has electric in it. I like that. It should be like magnetic displacement or something like that. I don't know. But it remains nameless. Here's the thing the reason he's resistant to giving it a name is other books call H the magnetic induction or sometimes the magnetic field. Now, in calling it magnetic induction is really obnoxious because when you talk about inductors and stuff, that just begs all kinds of unnecessary confusion, especially for introductory students. So, like the choices that have been made, basically the problem is other physics books and engineering books take the H to be fundamental. And there are reasons for doing that in terms of working with problems of magnetization in matter that make sense. But from a fundamental physics perspective, the magnetic field is basic, and it's bad to call the thing which is not basic the magnetic field. right? And then they'll say the magnetic field is like, I don't know, I can't read all books, right? But I'm just saying that there's an issue of language here. So when you open up another E&M book, be aware of this. Yeah? So if this is true, if we integrate this, right, over some surface, then what would be the integral of the free current density over the surface? Well, this is the current enclosed, right? And on the other side, we can do Stokes' theorem, and we trade the flux of the curl for the circulation of the auxiliary field, because I don't have a better name for it, around the edge. But there you go. That's basically the integral form of Ampere's law for the auxiliary field. Notice the absence of the permeability. All right. So an example we can look at. So suppose you have a cylinder of radius r, all right? And we have current I flowing uniformly along the axis, along the line of the cylinder. Let me draw a picture. What we want to do is we want to calculate let's calculate H both within and without, like inside and outside rather, of the cylinder. So my cylinder, what is this example? 3. So I'll draw two pictures. First picture, second picture, and I'm going to draw an Amperian loop, and this one inside. And over here, I'm going to draw the Amperian loop outside. So here, of course, the current enclosed is just that part, all right? So this distance here we'll call S. All right, S. Now, of course, if I draw, like the circle of the cylinder out here, right? I'm supposing that its radius is r. That's given. All right. So in contrast over here, now, and don't worry, it's about to be over. So the current I is flowing uniformly through this tube. It's a solid tube. I is uniformly distributed going upward, okay? So like in this one, I enclosed is what? I, it's the whole deal. In this one, on the other hand, I enclosed, we can use a fraction. We got pi s squared divided by pi r squared. That fraction, that portion of the total current goes through that, is enclosed by that Amperian loop. Now here, of course, we've got 0 less than or equal to s less than or equal to r for this case. And over here, we're talking about s greater than or equal to r. And so again, s is here. Right, whereas s was here. Okay, yeah, did I do something? No, okay. So then we have the integral. Oh, b, no b. H dot dl is equal to s squared I over r squared. Right? But by the symmetry of the problem, this is also equal to 2 pi s times H. And over here, we likewise get the integral of H dot dl is equal to I. So we get 2 pi s h is equal to I. So in summary, we have the following formulas. H is equal to, apparently, S I divided by 2 pi r squared. See the s squared and the s be canceling? And then outside, we got ourselves an I divided by 2 pi s. And for both of these, the direction is simply phi hat. Now, I cannot say with authority what the value of the magnetic field is within the cylinder, because I haven't said what the magnetization is of the cylinder. See, I would need to know what the magnetization is in order to get the magnetic field from the auxiliary field. Remember that we have H is 1 over mu naught B minus M. So that we can solve for the magnetic field is actually equal to, mu naught H, right? Plus M, yeah? That's nice to know about. So once we know H, we can recover the magnetic field if we know the magnetization. Now we do know the magnetization outside, right? For S greater than or equal to R, we have what? What's the magnetization out there? Outside of 0, right? Because it's free space. We're assuming, we always assume vacuum unless otherwise stated. So 0 out there. And so what's the magnetic field? Well, the magnetic field then is, unsurprisingly, mu naught I over 2 pi s phi hat. Of course, it had to be that, right? Because we could have applied Ampere's law and discerned that with our previous methods, right? That had to happen. Now, I can't solve for the magnetic field inside until I tell you what the magnetization is. But if I told you what the magnetization was, if we had it, if it was given, then we could just find B as well. All right? So that brings me to my last slide for today, page for today, which I guess I'll do here. Whee! So you guys remember we talked about linear media? Remember that? Linear media. So we can talk about that here as well. Linear media. And basically, yet another definition. Magnetization is equal to the susceptibility, the magnetic susceptibility, chi-m, times the auxiliary field, H. So you might have expected me to put a B there, right? That's more or less what Griffiths is like. You might expect to have a B here, but no, it's H. And that just reflects the fact that the people who invented this stuff thought of H as primary. So it's kind of a historical artifact that it's defined this way. But anyway, that's the definition, so we deal with it. And then we have, we'll look at it. The magnetic field is mu naught H, right, plus M, which is apparently mu naught H plus chi-m H, right? Which is what? Mu naught plus, I think I lost a mu naught. Whoa, dudes. Did I lose a mu naught over here? Was this supposed to have a... Oh, there's a parentheses here, guys. Don't let me do that. Now these poor people on YouTube, they're going to make a comment feeling righteous indignation about my lack of parentheses here, only to find out, much to their chagrin, that 3 minutes later in the video, we had parentheses, you know? Now, if I was a better YouTuber, I would make a comment about this so they could find it beforehand, but I think I'm just going to let it sit. Anyway, so this is parentheses here. Parentheses, right? So what we have is mu naught times 1 plus chi m times h. So, well, I have one definition when you can have three. We'll let mu equal to mu naught times 1 plus chi m. This right here is the so-called permeability of the media, of the material in question, all right? And you can see that in terms of this, we have the formula B is equal to mu h. So finally, let's go back up to this susceptibility. There's another comment I should make here. There's two things we could say. Chi m positive, chi m negative. This would say material is what? Fill in the blank. Material is fill in the blank. Yeah, which one is paramagnetic? Which one is diamagnetic?
Diamagnetic would be negative.
Very good. Because that means that the diamagnetic, that means that the, you know, the induced field is opposite. But yeah, that's diamagnetic, and the positive is paramagnetic. And if you look in Griffiths, he has like a table with some common examples of both, which I mentioned earlier today. Right. So the last thing to discuss is just like what's ferromagnetism. And that's like a much more complicated discussion, honestly. Like I can just kind of give you a sense of it, but basically the thing is, with something like iron, it kind of like crystallizes in some sense. It gets locked into like blocks of sorts, you know. So maybe this is your iron, right? And then you get some like regions in there that these regions, they tend to like all align, like the atoms end up just aligning in that region and then in that region and then that region. And if you apply magnetic field, enough of it, eventually you can get the different chunks to all align. So, but it locks up, it like locks in such a way that the paramagnets and the diamagnetic things don't do. There's something special about the ferromagnetic material where it locks in the magnetization. And it doesn't, and it's a complicated thing too. Like it depends on the history of how it's done. There's something called a hysteresis loop, and he talks through it like a whole page of like the process of magnetizing iron, reaching a saturation point, and then like putting the field in the opposite direction, how you go back, and it's a complicated business, and it's somewhat, it involves phase change. Like there's, a real physicist could talk about ferromagnets for weeks. There's all kinds of like detailed, deep statistical mechanics stuff in there. So that's not me. Sorry, guys. But I would encourage you to read the 2 pages in Griffiths. You'll be much more knowledgeable about it than I am if you do that. But anyway, enjoy your break. I think that's it.